How was job fair? Yay? No? 2 thumbs up? So, I did lecture on Wednesday, even though the class was a little sparse, but because Lab 2 is upon us, what I talked about was 2 topics, really. One was the state machine necessary for debouncing the keypad, and the other topic was understanding homework 2. So you should probably watch the video notes. I believe it was up as of yesterday. But are there any questions about that lecture that you saw on video note? Possibly. Otherwise, I'll do questions on Monday. Yeah.
I asked you about this in lab yesterday, and you told me to bring it up. In the MATLAB code for homework 2, number 1, there's a variable called steps per cycle.
And it's really steps per window.
Yeah.
Yes.
It's total steps.
It's
steps per cycle.
Totally stepped. Okay, let me find that here. This MATLAB program has is an attempt to understand the spectrum of a sampled square wave. That's a horrible drawing, but understand the sample of the spectrum of this square wave, of this sine wave. And it is modeled in the MATLAB program as if you are calculating samples of a sine wave and then outputting them through a zero-hold DAC. In other words, the DAC holds a constant value until you put in a new value, and then it holds that value until you put in the next value. That is how the DAC we're using operates. You put in a sample, it holds the sample. It doesn't interpolate, doesn't do anything fancy, just holds the sample. So if you were to sample a sine wave at a finite number of points, the waveform which came out of the DAC would actually be a stepwise approximation of the sine wave, which is equivalent now, thinking back to 2200, it's equivalent to modulating a sine wave by a square wave, multiplying them together. And so the spectrum gets complicated. And the reason for bringing this up is that crickets make a relatively pure sine wave. I would like the sine wave you synthesize to have all of the error terms, all of the bogus spectral components, 20 dBs down from the true frequency you're trying to generate. So see, all spurious frequencies must be minus 20 dBs from the main tone. 20 dB is a factor of 10. All right. And that's over a range of 1 kilohertz to 6 kilohertz. So if we take a normalized image, normalized to 1 cycle, I don't care what frequency it is, it's 1 cycle. 1 cycle of 6 kilohertz, 1 cycle of 4 kilohertz, 1 cycle of 2 kilohertz. Whatever it is, it's 1 cycle. If we have 8 samples on that 1 cycle, then the spectrum is going to look like the true frequency, in this case exactly 1 per window, and then error terms that start right around the number of steps per cycle. So in this case about 8. And so the question is, could you hear that? Would that sound good, or would it sound schnasty? Would it sound raspy and ugly? That's what you're going to have to determine, either by trial and error or by just making the system good enough that it doesn't matter. Now, so we go to 16 samples. You say, oh, that's much more pleasing. If you do the old chi by eye, you squint at that. Yeah, you use your eyelashes as a low-pass filter, right? Then works. And then, so you can you can get a much better feel for a sine wave, and sure enough, the error terms are smaller relative to the peak. By the way, I didn't plot dBs here, I plotted log units, because I like log units better. So each log unit is 20 dBs. So this is about a little over 1 log unit down in error term. And by the time you go to 32 samples per cycle, it's way down. So you're going to have to play around a little bit with this. I'm not going to tell you how fast you have to sample it. You're going to listen to it. You're going to use some intuition. You're going to use your signal processing background. This is, after all, a CDE class. I can ask you anything from 4 years. And I just found out that Abed is grading me on how many math questions I ask you. So you're going to have to do a little bit of analysis. Now, by the time if this frequency is about 16 times, the first error frequency is about 16 times the fundamental, you could low pass filter the signal and get rid of a lot of that modulation artifact. It's 16 times the frequency. That's easy to do with a RC low pass filter, which has a characteristic that looks like this. If this is log F and this is log amplitude, you have a cutoff frequency around here. The slope of the asymptotic slope is minus 20 dBs, or an order of magnitude in amplitude for an order of magnitude in frequency. That's the same as saying minus 20 dBs. So if you set this point a factor of 10 above the sample frequency, you'll lose about 1 order of magnitude of noise. That's a good thing. So you have a trade-off. Sample faster, do some filtering. The advantage of sampling faster is it's pretty easy. The disadvantage is you sample fast enough, you run out of CPU. And that will happen someplace between 100,000 and 1,000,000 samples per second, depending on the arithmetic you do in the interrupt service routine. So there's some design to do here, but the idea is for you to think about how good does it have to be? Is there any other questions on this right now? So let's go back. Oh yes. Oh yeah. Let's go back and look at lab 2 now. I haven't actually gone through the assignment yet. You probably have read this, but just in case you haven't, I'm going to ask you to use direct digital synthesis to make sine waves. So given that you want to build a sine wave out of a finite number of samples, how do you choose those samples? And direct digital synthesis is a scheme for easily generating sine waves of very carefully controlled frequencies from one table. For any given for all frequencies, you have just one table and really simple arithmetic. As we talked about in some horrible detail last time, the LCD and keypad are going to be used to enter arbitrary combinations of 5 parameters. And one thing I didn't talk about, the state machine I talked about last time gives you a good guess about which buttons were pushed. So if the oh-so-slow human presses 4 and then 200 cycles of the state machine later presses 5 and then presses 3 and then enter, probably the pound sign, the debound state machine will reliably give you the 3 digits plus the enter. Then what do? How do you make that into an integer? You've got 3 disembodied decimal digits, but it could be 4 or 2. So how do you turn that into an integer? What would be a good way to do that?
Use A2I.
Oh, so you could make a string 4, 5, 3, 0, because a C string always ends in a 0, right? And use A to I. You could do that, except those aren't ASCII digits.
You just added a small offset.
In fact, it's hexadecimal 20 that you add. So if you add hexadecimal 20 to each of these numbers, so if you add hexadecimal 20 to each of these digits, except the last one, the 0, the terminator, then you can use A to I, which is, what's it stands? ASCII to integer, I guess, is what it stands for, ASCII to number. It's in standard lib. That'll certainly work, given that you add the offset, the ASCII offset. Y'all know about ASCII code? Yeah? That's common terminology, yes, no? There's another way to do it, which may be even easier. Every time you enter another digit, you multiply all the ones before that by 10. So you enter 4. When you enter the 5, you say, oops, it's now 40 plus 5. You enter the 3, it's now 45 times 10, 450 plus 3. So you can do it on the fly by just taking the partial sum and multiplying it by 10 and adding another digit. Lots of ways to do it, but think about how you're going to put together this number to make a command. Another thing that I thought about after talking about the keypad, remember the keypad is going to be driven a couple of logical days ago, Monday, we talked about this driving system for the keypad. It's going to be A0 through A3 and B7, B8, and B9 is what you're going to read off the keyboard. I figured, oh my goodness, last year we didn't use these pre-built boards. We had students roll their own wires to the keypad. What if Sean wired some of these wires to vital functions on his big board and now you can't use them? So, went back and looked at the documentation for the big board. Nope, yep. Pick 32 target boards. We scroll down a ways here, and we find that I thoughtfully sorted all of the signals used by port number here so you could figure out what's already in use. Oh crap, RA0, RA2, and RA3 are already in use. Or are they? Are they on your board? Are they? Are you using the LED? Yep. You got the port expander put in? Come on. Look alive, folks. Is the what?
There's nothing in it.
Yeah.
There's nothing in the socket. Therefore, these are all disconnected. And you can use them any way you want. Uh-oh. RB9 is on the list also. Oh, but it's on the port expander, SPI, chip select. You don't have the port expanders plugged in. It doesn't matter. That only leaves RA0. Does it matter that the LED is also hooked to RA0 if it's an output? No. The only thing that will happen is you'll have an error detection. The LED will blink blah, 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 when you're scanning the keyboard. Blink, 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 blink. That's handy. That's not a bug, that's a feature. So since you did not plug in the port expander, all of the lines are available to use as you would wish to use them. What if you had plugged in the port expander? What would you do? Use the port expander. That's what it's for. It gives you 16 extra I/O lines. By next year, I will have coded up a port expander example which includes the keypad. But this year I didn't get to it. So, all the documentation, I believe, is self-consistent, and therefore the lab is doable as written. I'm going to ask you to have all time intervals and burst duration accuracy should be plus or minus 1 millisecond. That's so you can use the tick timer in proto-threads for timing events. Each sine wave burst has to be amplitude modulated from 0 to full amplitude in 4 or 5 milliseconds. There can be separate control buttons for play, stop, and test, and those do not have to be on the keypad. It is possible to make a shift key on the keypad so you can double the number of functions. It is just really annoying to do that. So you can add to the keypad, you can have 3 extra buttons, start, stop, and test, that you can add to a whiteboard to control this system. Start is going to do what you think. It's going to play the cricket call forever. Stop stops it. And test produces the frequency that you have the burst frequency set to, indefinitely as long as you hold down the test button. That is because it takes the oscilloscope a second or two to acquire the FFT that you need to prove to the TAs that the frequency is correct and the harmonic distortion is low enough. So when you're demoing this to the TAs, then you'll set it to 4 kilohertz or 6 kilohertz. You'll press the test button, and the TA will look for the spectrum equivalent to what was in the homework to make sure that the loudest component is an order of magnitude down from the fundamental. Frequency accuracy should be plus or minus 1%. I already said that. You're going to need to connect a speaker output. And this will also be useful for debugging. So you don't want to do this last. You're going to want to do this soon. And anything that sounds like a click or a pop will be an artifact that should be gotten rid of. So any discontinuity in the waveform. Your waveform is sitting at 0. You press play. Bam! The voltage comes up to 1 volt and then starts a sine wave. That discontinuity when you press start, if there is a discontinuity when you press start, that'll acoustically be a click. It'll be a loud pop, which will annoy the TAs and me. So avoid large discontinuities in the waveform. Avoid any discontinuity in the waveform. Any questions on the specs? So we've talked now about, yes?
Do the play and stop buttons have to be separate? Like a toggle?
You could definitely do a toggle, then you have to debounce them.
I see.
Because if you don't debounce, you'll press play and it'll go play stop.
Right. Right, that makes sense.
So by having separate buttons, you don't have to debounce.
Yeah. You just ignore the second play.
Exactly. Right. So then one piece of this is the keyboard scanner and the parameter setter. The piece we haven't talked about yet is the synthesis piece. And there's really going to be several steps in the synthesis. One is DDS, which I've talked about some, and I'm going to show you an example of very soon. Then there has to be an envelope, VLOPE, envelope generator that turns the sine wave into a burst. And then you may have to scale the whole thing depending on exactly how you've done the arithmetic, because the DAC is going to have a range of 0 to 409097, 2 to the 12th minus 1. You may have to scale it. Then you are going to dump the data to an SPI DAC, digital analog converter. Then once you get out of, then once you're in analog domain, so here down is analog, you may want to filter. I don't believe you'll have to amplify, and then go to speakers. The speakers we have are amplified speakers. So this is digital. This is in an interrupt service routine, and has to be an interrupt service routine because you're going to have to do it lots, more than 40,000 times a second. So let's start with some direct digital synthesis. And the goal here is to figure out how to optimally choose entries from a table of sine. So you're going to have a table of 256 sine values corresponding to index 0 to 255 will be 2 pi. We'll scale to 2 pi. And the amplitude you're probably going to want to set to like 2047 plus or minus 2047. 2047. And you're going to, and what you'll have here then is 256 samples. You're going to want to choose samples from that sine wave to output to the DAC, and you have to choose at least 8 or 16 per cycle of the sine wave. So 30 or 40 years ago, somebody thought up this system which goes like this. And the central abstraction is that a variable overflow is topologically equivalent to one rotation of a phasor. How's that for abstract? So if you think of a sine wave being generated as we do in back in theory class someplace, as the projection on the axis of a rotating process, a phasor, then after 360 degrees you go back to 0. With a 32-bit register, after 2 to the 32 counts, you'll go back to 0. So what we're going to do is we're going to map one overflow of this 32-bit register will be mapped to one cycle of the phasor. And so every time you overflow the register, you'll generate one cycle of the sine wave. The top 8 bits of this register, the top 8 bits of the variable, are going to then be used as an index into a sine table. So we're going to keep a 32 bits running sum where the value here will be added, not in hardware, although it could be, is going to be added to an increment that you're going to choose, and I'll show you how to choose that. and then fed back into this variable. So on every time step, you're going to increment the phasor angle by one step of the sine wave that you want to output. The more angles you choose, the more accurate the approximation. So, to show just a little bit of code, maybe make this more concrete. Aha, I haven't updated this. I haven't refreshed this recently because I changed the example this morning in Lab 2 because I didn't like my old example. So there's the new example uses the first bunch of stuff is set up for the DAC, and I don't want to talk about that just yet, but I will soon. And then we're going to go directly into the interrupt service routine that generates the direct digital synthesis. And the entire direct digital synthesis algorithm is 2 lines. Phase accumulator equals phase accumulator plus increment. That steps the phasor angle around the unit circle. Ding, 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 all the way around the unit circle. And then the second line takes the top 8 bits of the phase accumulator by right shifting 24 bits and looking at a sine table. That sine table entry then will be output directly to the DAC with some offset to make sure it's positive and some other things. But the whole algorithm is increment the accumulator to get a new phase angle, and then use the phase angle to look up the sine value. This, for some reason, I've never quite figured out, this worries people a lot. It seems too simple or something. I'm not quite sure what. There's a bunch of implications of this, though. First of all, people ask, why 32 bits if you're only going to use 8 bits? Is anybody going to ask that? Yet? Okay. And the reason is, you want to be able to step through the table by a fractional index. Which is to say, at low frequencies, you're not going to take a new value of the table every sample. You're going to reuse the last sample at low frequencies. You only have 256 entries. If you're sampling it a cycle per year, you're going to have a lot of copies of the same sample before you go to the next sample. Having lots of bits gives you better frequency resolution. So how do you choose? So how do we? What frequency is what? Well, let's say we have a sample frequency of fs, and we have 2 to the 32 states we're going to go through. Let's say we're toggling every 100,000 times a second. We're incrementing the phasor. What is the frequency at which the phasor increments if we increment by 1? The phasor overflows. In other words, we get 1 cycle of the output sine wave. Every time this goes around once, we get one cycle of the output sine wave. And if we're incrementing by 1, if the increment equals 1, then we will overflow at the sample frequency divided by 2 to the 32. It takes 232 counts to make one complete traverse of the register. So that for an increment of 1, the output sine wave frequency will be some really low number, like 1/1000th of a hertz or so, depending on the sample frequency. Let's say we increment by 2. What happens to the frequency of the output? Doubles. You're incrementing the phasor twice as fast. The phasor is going around this loop twice as fast, which is equivalent to saying we have a sample, we have a frequency twice as high. So for a general increment, if increment is generalized, then we'll say that F out is equal to Fs over 2 to the 32 times the increment. So the sine wave we generate, F out, will be related to the sample frequency and the increment in this fashion. If we go to a big enough increment, we will no longer go through the table one entry at a time. We may skip entries. That's okay. You can skip entries as long as you skip the correct entries. So you can set the frequency then. Let's say that I'm asking you to produce a cricket call of 3,500 hertz. So you're going to think in hertz because that's what the specification is going to be in. We want to find out how to synthesize 3,500 hertz. We want to find out the sample interval for 3,500 hertz. We need the increment. We just rearrange this. And we get that the increment necessary is equal to F out times 2 to the 32 over the sample frequency. You're controlling everything. You know the sample. You're choosing the sample frequency. You're choosing F out, therefore you know the increment, so you know how fast you have to rotate this phasor to get the frequency you want. So if we look at the code, we'll see that down here in the thread, there's only one thread in this example. And every 100 milliseconds, I'm choosing a new sine wave F out in such a way that it scans from 400 to 4,000 hertz. And it does that on a logarithmic scale or exponential scale. Every time through the loop, every time through this thread, it's incrementing the frequency out by a factor of 1.05. So you get this kind of uniform frequency sweep from 400 hertz to 4 kilohertz as an example. And it gets to 4 kilohertz and I do a reset and it starts over again. F out, then the increment that we use for the DDS routine is just the integer value of F out times 2 to the 32 divided by Fs. 2 to the 32 is a macro that has a value of 2 to the 32. So setting this up for a given frequency is quite easy. It's a total of like 3 lines of code. But for some reason this bothers people. I've never been quite sure why. Are you bothered by this? Are you worried that you're not using every sample in the table? What worries you about this? Well, you won't be worried until you actually try and program it. Then you'll be worried. But hopefully the example will help. And this example then also shows how to set up the serial peripheral interface to control the DAC, and I suppose we need to talk about that now a little bit. Oh yes, one other thing in this. We need the table. So in main we set up a table, although we could have done it in a thread. The table is a mess of, it's a 256 entry table scaled to 2047. So the sine wave amplitude is plus or minus 2047. The rest of this just makes sure that you fill the array with one cycle worth. However, this goes up plus 2047 minus 2047. The DAC requires a strictly positive number between 0 and 4096. So why didn't I just make the table 0 to 4096? The reason is that when you are modulating this function, when you're actually making a amplitude dependency, you want 0 amplitude to map to 0 output. So the sine wave is going to be, the mathematical sine wave is going to be plus or minus 2047. Your envelope is going to look like this. Starts at 0, goes to 1. It would be nice if when you did the multiply of 0 times 0, you got 0. One way to do that is to make sure that the entry here is 0 and not plus 2047. So my code uses a zero-based table rather than a offset table, and the offset to compensate for the requirements of the DAC are done at the very last step. You take the data and you offset it. So that's after all the multiplies are done, all of the scaling is done, then you bump it up to full scale over 2 to center it in the range of the DAC. So let's just think about resolution here a little bit. Let's say that we have let's go back to an increment of 1. An increment equals 1. So we're going to ask now, what is the resolution of counters of different lengths? And let's say we're going to sample at a sample frequency of fs equals 2 to the 17th. That's 128,000 samples a second. That's in a reasonable range. And that we have a 32-bit register, so we're using an int to store the accumulator. Then 2 to the 17th over 2 to the 32 is the frequency out you'll get for an increment of 1. And that corresponds to what? 2 to the minus 15 hertz. That is the resolution of your synthesizer. You add another increment, it'll go up to 2 times 10 to the minus 15th. You add another increment, it'll go up to 3 times 10 to the minus 15th. This is a really fine frequency control. In fact, it's ridiculously fine. So what would happen if we kept the sample frequency the same, but we went to a short? Now, the frequency resolution is going to be 2 to the 17th over 2 to the 16th, or about 2 hertz. Is that good enough for this lab? Got to have within 1% frequency at 1,000 hertz. Is it good enough? Yes. So you could use a short accumulator rather than an int. But let's say you say, well, why do we have all those extra bits? What would be the resolution if we just used the upper byte? If we just had a 1 byte accumulator? Because after all, we only have 2 to the 8th entries in our table. Why don't we just use a 1 byte accumulator? If we do that, then at fs equals 128 kilohertz, 2 to the 17th, and then we have 2 to the 17th over 2 to the 8th. So the resolution is 2 to the 9th, or 500 hertz. So a short or a car accumulator will not work because you won't have the frequency resolution. A short will just barely work, and an int will easily work. So I'm going to want you to program up direct digital synthesis, take the sine wave values, scale them by an envelope, and output them to the DAC. What shape should the envelope actually be? You could ramp the amplitude up, ramp it down. You could use an exponential rise and an exponential fall. You could use a Hanning window. Remember that? Didn't you do windowing in 2200? No?
I think only in DSP.
Oh, really?
We start 2200 and talk about it.
No, only in DSP? What course number is that?
4250.
42? Wow. So you don't actually see that until like senior year? Okay. All right, so a Hanning window looks something like this. It looks like a cosine, a raised cosine, or a raised or cosine squared. So you multiply the sine wave by a ramp, you get a linear increase. By an exponential, you get a rather fast rise and then a slower rise. And by a Hanning window, you start off very smoothly, go up and go down smoothly. The advantage of this is the bandwidth is very narrow. The disadvantage is it's hard to calculate the rise and fall times. This is easier to calculate the rise and fall times, but the spectral spread is not as good. This I'm not even sure about for spectrum. Haven't worked it through. So you're going to have to choose a modulation to make a burst. You have to choose a modulation method. I suggest, for sanity's sake, you use a linear ramp up and a linear ramp down. However, there is one other option which is kind of interesting, and that is right shifting the whole waveform in small steps. So so you start out with right shifted 5 bits, and then 4 bits, then 3 bits, then 2 bits, then 1 bit. So you take the sine wave, you right shift it a lot, you get a low amplitude. You right shift it 1 less bit, you get a higher amplitude by a factor of 2, 3 dBs. And so by right shifting less and less, so this is right shift 5, 4, 3, 2, 1, 0. By right shifting less, you get a higher amplitude by a factor of 2 every time. You get an exponential rise. The arithmetic is extremely cheap, and it actually sounds rather good because your ear has an exponential response. Your ear is not linear with amplitude. It responds to the log of the amplitude. And so by making exponential steps, it sounds like a linear ramp. So that's a possibility instead of using a per sample linear ramp. What you're going to have to do is you're going to have to get the synthesizer running and listen to it. So one person in the group can get the keyboard thread working. The other person in the group can get the synthesizer working, perhaps in simulation, perhaps in MATLAB, and listen to it. Does it click? Does it sound like a cricket? Do any of you know what a cricket sounds like? It turns out it depends on where you grew up, what a cricket sounds like, because crickets around the world sound different, very different. But you're going to want to listen to the synthesis to try and figure out if it's working right. Your ear is amazingly good at detecting sequences, way better than your eyes. So, direct digital synthesis, modulation of the sine wave by some function that you choose, probably linear, output to the DAC, which we haven't talked about yet, but these are serial peripheral interface commands. Output to the DAC, probably analog filtering, using a passive filter probably, although at least one person will probably build an active filter. And then speaker output. Mull this over the weekend, come back on Monday with questions. It's an easy algorithm that people find confusing, and if I could figure out why, I'd change the pitch. But I don't know why. Now, there's an occupational hazard that goes along with teaching the same thing 20 years in a row. Everything gets easy. And then you forget why it's so damn hard. Right. And so this may be my bias. But in any case, look at the direct digital synthesis stuff. Maybe even write a little bit of code to play with it. For now, you can treat the SPI as a black box, but we will go into that. So, Friday. So who's got a keyboard working already? You got a keyboard working? I saw people. Yeah, you got a keyboard working. Good. I saw a couple of people had gotten keyboards out. Any problems with the keyboard? It just worked?
Yeah.
Good.
You can't put two buttons together.
You can?
Yeah, because the display will be wrong. You put two buttons together.
Well, if you push two buttons, the table should filter that out.
Yeah.
It should tell you that it's a null, right? And remember, there's an error in my code. There's a missing. Where was that? If we go to the keypad test code, the thread which scans the keypad every 30 milliseconds returns an incorrect value if you press 2 buttons because I did not initialize the index to -1. So the index should be, I set it to -1 if nothing was pushed, but I should have set it to -1 so that if there was no table match, it also was -1. And this, what did it return if you press 2 buttons? 12, right, which is wrong. I suppose you could down here you could say, if I equals 12, I equals -1. That's crude, but that would work. Okay, I will see you in lab in a few minutes.